Welcome back to The Explainer. Today we're unpacking a newly published, genuinely mind-blowing discovery that could completely redefine how we power our lives. Imagine if you could literally bottle the sun, not as electricity stored away in some heavy battery, but as pure, on-demand heat. Well, today we're opening up the research notebook on a breakthrough that does exactly that.
To understand why this matters right now, we gotta look at one staggering number, 50%. Yeah, a full 50% of all global energy consumption goes directly toward heating. And here's the kicker, nearly 2/3 of that heat still relies on burning dirty fossil fuels like natural gas, oil, and coal. We talk a lot about clean electricity, but you know what? We actually have a massive, totally overlooked clean heat crisis on our hands.
But a potential solution just dropped in a groundbreaking new paper published in the highly prestigious journal Science. This is a big deal. Led by researchers Han P. Kyun Wen, Grace G. D. Han, and K. N. Hauk, the paper is titled Molecular Solar Thermal Energy Storage in Dewar Pyrimidone Beyond 1.6 megajoules per kilogram. Okay, I know that is quite a mouthful, but what they're actually proposing here is a radical, totally chemical solution to our global heating problem.
Okay, let's dive into this. The core of their discovery revolves around something called MOST, which stands for Molecular Solar Thermal Energy Storage. Think of MOST as a way to physically capture the photon energy from sunlight and literally lock it directly inside the chemical bonds of a molecule. Later on, you can trigger that molecule to release the energy as heat. So we're not generating electricity to run a space heater here, we are bottling up sunlight to use as pure, on-demand thermal energy. It's wild.
The whole system works a lot like a microscopic molecular spring. First, the molecule catches UV light from the sun. The energy from that light forces the molecule to change its shape, winding its chemical bonds up incredibly tight. And that's how it stores the energy. When you actually need the heat, you simply introduce a trigger, in this case, an acid. That trigger violently uncoils the spring, and all that trapped solar energy is instantly dumped out as intense heat. Now you might be wondering, how do the researchers know how to build this specific molecular spring in the first place? Well, they acted like science detectives, taking their inspiration from a rather unexpected place: DNA damage. See, when human DNA is exposed to high-energy UV light, it can create these strained, damaged bonds, mutations that can actually lead to cancer. The scientists looked at that exact mechanism, isolated how the UV light forces those chemical bonds into a tight, strained state, and then successfully applied it to a completely synthetic molecule.
And as you'll see with the physical transformation itself, it's pretty remarkable. On the left, you have the relaxed, stable molecule known as 2-pyrimidone. But expose it to UV light, and it snaps right into the shape on the right. It's highly strained, energy-packed form called a Dewar isomer. You can physically see how those bonds have been forced into a tighter, almost unnatural-looking box shape. That structural tension right there, that is literally trapped solar power.
By brilliantly tweaking the atomic structure of this molecule, specifically placing methyl groups at certain optimal positions, they achieved something genuinely historic. This molecule can store 1.65 megajoules of energy per kilogram. That is a record-breaking energy density, completely blowing past previous MOST systems that always kind of struggled to hold enough energy to be truly useful.
But here's the absolutely crucial point. They didn't just make a powerful molecule, they made a highly practical one. In the past, most systems often required toxic or super complex solvents just to work. But this team engineered their specific molecular structure for completely solvent-free operation, meaning it has perfect compatibility with regular, everyday water under ambient conditions. That solves a massive, massive limitation of past research. To prove just how powerful this really is, they set up a physical demonstration. The stakes? Trying to boil water using absolutely nothing but this solar-charged powder. And look at the incredibly tiny amounts we're talking about here. Just 107 milligrams of the charged Dewar pyrimidone powder dropped into a mere 0.46 milliliters of water. We're talking about a literal pinch of dust in just a few tiny drops of water.
So when they added a tiny bit of acid catalyst to trigger the reaction, the result was absolutely breathtaking. The temperature of the solution shot straight up to 100 degrees Celsius and induced full boiling in just one single second. Seriously, 1 second! From room temperature to a rolling boil just by releasing the chemical tension stored up from the sun.
And this brilliantly illustrates the hard data behind that massive heat spike. Using differential scanning calorimetry, which is a highly precise way to measure heat absorption and release, we can actually map the reaction.
See that massive, sharp red peak? That is the sudden explosive release of heat. And honestly, the best part? The whole cycle is fully reversible. Once the heat is released, the molecule uncoils back to its relaxed state, perfectly ready to be recharged by the sun and used all over again.
So, what does this all mean for the real world? Well, to be fair, we do still have to figure out the major engineering challenges of producing this chemical on a massive industrial scale. But the potential here is staggering. We're looking at a future of scalable, off-grid water heating, clean cooking technologies for developing nations, and even on-demand surface defrosting for things like airplane wings or wind turbines. It's a sustainable, zero-emission way to deliver intense heat exactly when and where you need it, long after the sun has actually set.
We are literally learning how to copy DNA's mistakes to bottle sunlight. It's an eccentric, completely genius approach, and it's exactly the kind of out-of-the-box breakthrough we need to solve our clean heat crisis. So I'll leave you with this. As this incredible chemistry finally moves out of the research notebook and into our energy grid, how will bottled sunlight change the way you heat your world?